Let us look at proposition number 9 of works of Archimedes, specifically from on conoids and spheroids. The proposition says, given an ellipse, a plane through one of its axes and perpendicular to that of the ellipse, and a straight line CO drawn from the center C of the ellipse in the given plane through the axis but not perpendicular to that axis, it is possible to find a cylinder with axis OC such that the ellipse is a section of it. So basically, we have to arrive at a cylinder, axis is OC, and the surface of that cylinder passes through this ellipse. So let's see how we can go about doing that. Given an ellipse perpendicular to the plane of the paper with A prime the major axis and BB prime the minor axis, and see the center. Take a point in the plane through A prime perpendicular to the plane of the ellipse such that OC is not perpendicular to A prime. Draw AD and A prime E parallel to OC. AD and A prime E, and they are both parallel to OC. Draw DE through O perpendicular to both AD and A prime E. So here, how do we decide where D will be? Whether AD will be this or up to here. A prime E will be up to here or up to here. That we decide based on this line, D. We draw a line through O perpendicular to both AD and A prime E. DE, BB prime may be equal to DE, greater than DE or less than DE. So let's take these cases one by one. So case 1 is BB prime is equal to DE. Draw a plane through DE perpendicular to OC. Describe a circle with DE as the diameter in the above plane. So in this plane, DE we treat it as a diameter and draw a circle around it. Draw the circle on DE. Describe a cylinder with axis OC and height equal to AD. This would be the cylinder whose surface passes through the given ellipse. But we have to prove it, right? So let's see how we can prove this. Let P be any point on the ellipse. Draw Pn perpendicular to A prime. To N, draw Nm parallel to CO, meeting DE at M. In the plane of the circle on DE, draw NQ perpendicular to DE. We draw MQ perpendicular to DE. So let me show you that circle again, meeting the circle at Q. Pn square is to An times Na prime is equal to Do square is to AC times Ca prime. How did we get this? Because remember, Pn square is to An times Na prime is equal to Bc square is to AC times Ca prime. Bb prime is equal to De. That means Bc is equal to Do. So we can say Do square is to AC times Ca prime. And Dm times Me is to An times Na prime is equal to Do square is to AC square, which means Pn square is equal to Dm times Me. How? Because Pn square is to An times Na prime is equal to Do square is to AC times Ca prime, right? And AC times Ca prime, they are both equal. So we can write that as AC square. So Do square is to AC square, right hand sides are equal in these two. So we can say Pn square is to An times Na prime is equal to Dm times Me is to An times Na prime. And since Pn square and Dm times Me, they have the same ratio with a third quantity. So which means Pn square is equal to Dm times Me, which means Pn square is equal to Qm square, because Dm times Me is equal to Qm square. Now, since Pn square is equal to Qm square, it means Pn is equal to Qm, which means PQ is parallel to Mn, and M is parallel to OC based on construction, and Pn is equal to Qm. So, which means PQ is parallel to Mn. So that means PQ is a generator of the cylinder. So if I move this P, remember P is any point on the ellipse. So at all points, this statement will be true. So PQ is a generator of the cylinder. Let me show you by actually bringing back that cylinder. So we can say PQ is a generator of the cylinder, and that means surface of the cylinder generated passes through P and hence the ellipse. So that was the first case. Now let's look at the second case. Now in this case, BB prime is greater than DE. So if we can somehow make this line equal to BB prime, the same logic we can use as in the previous case. So for that, what we'll do is take a point E prime on extended A prime E such that BB prime is equal to DE prime. So we extend A prime E so that DE prime becomes equal to BB prime. And we extend CO to meet DE prime at H. Draw a plane through DE prime perpendicular to the plane of the paper. So let's draw that perpendicular plane. And in this plane, we describe a circle with DE prime as the diameter. To the circle on DE prime, we describe a cylinder with axis OC, or we can take HC as well, or any extended points on this line as the axis, and we draw the cylinder. So again, I can't really draw the cylinder itself. So what I'm going to do is generate it. So this is the required cylinder, and this cylinder, the surface of it passes through the circumference of the ellipse. Now we have to prove that fact, that cylinder passes through the circumference of the ellipse. So for that, we take a point P on the ellipse. Draw Pn perpendicular to A prime. Draw Nm through N parallel to CH, meeting DE prime at M. In the plane of the circle on DE prime, draw MQ perpendicular to DE prime, meeting the circle at Q. Pn square is to An times Na prime is equal to dH square is to AC times Cs prime. How did we get this? Because remember, DE prime is equal to BB prime. That means BC is equal to DH. Now, BC square is equal to AC times CA prime. Since DH is equal to BC, we can say DH square is equal to AC times CA prime. Since BC square is to AC times CA prime equal to Pn square is to An times Na prime, we can say Pn square is to an times na prime is equal to ds square is to ac times ca prime. dm times me prime is to an times na prime is equal to ds square is to ac square. Remember, AC times CA prime can be written as AC square because they are equal. And DX square is equal to BC square. DM times ME prime is equal to QM square. And QM square is to DM times ME prime is equal to DX square is to AC times CA prime. So combining all these, we can say dm times me prime is to an times na prime is equal to ds square is to ac square, which means pn square is equal to dm times me prime. Here, right hand sides are equal. That means left hand sides are equal. And here pn square and dm times me prime, they are both having the same ratio with the third magnitude. So since they have the same ratio with the third magnitude, they are equal to each other. So Pn square is equal to dm times me prime. Now dm times me prime is equal to qm square. So we can say Pn square is equal to qm square, which means Pn is equal to qm. Remember, we draw, or rather we drew nm parallel to ch or CO. So since Pn is equal to Qm, Nm is parallel to CO or CH. That means PQ is parallel to Nm and CO or CH. Which means, let me join PQ also. So which means PQ is a generator of the cylinder, and surface of the cylinder generated passes through P. So that is how we have arrived at this cylinder, which passes through the circumference of the ellipse. So this was the case where BB prime was greater than DE. Now we have to look at the third case. In the third case, BB prime is less than DE. So now we take a point K on CO produced such that DO square minus BC square is equal to OK square. So let's do that. From K, draw KR perpendicular to the plane of the paper such that KR is equal to BC. In the plane containing DE and OR, that is this plane contains both DE and OR. Describe a circle on DE as diameter. Through this circle, draw a cylinder with axis OC. Now, what we are saying is that this cylinder, the surface of it, passes through the circumference of the given ellipse. So now we have to prove that. So let's get rid of this cylinder. Let P be any point on the ellipse. Again, as usual, as in the previous cases, we draw Pn perpendicular to A prime. To N, draw Nm parallel to CO. In the plane of the circle on DE, draw NQ perpendicular to DE meeting the circle at Q. Draw QH perpendicular to NM produced. So we extend NM and we draw a perpendicular from Q. DO square minus BC square is equal to OK square. That's part of the construction. Now adding to both sides BC square, we get DO square is equal to OK square plus BC square. That means OR square is equal to OD square. Why? Because BC is equal to KR. So DO square is equal to OK square plus KR square. OK square plus KR square is OR square. So which means OR square is equal to OD square, which implies OR is equal to OD. Now QH is perpendicular to the plane containing AC and DE. Now, QH square is to QM square is equal to KR square is to OR square. Since these two triangles are similar to each other, let's take QM square. QM square is equal to DM times ME. And now since we want to relate it to PN, let's take the ratio of both left hand side and right hand side with AN times A prime N, because we know PN square is equal to AN times A prime N. So QM square is to AN times A prime N is equal to DM times ME is to AN times A prime N. DM times ME is to AN times A prime N will be the same ratio as OD times OE is to AC times A prime C. Why? Because DM times ME is equal to QM square and DO times OE is equal to OR square. So which means that their ratios, these two ratios will be same. And same is the case with here. And OD times OE is OD square. AC times A prime C is equal to AC square. Let's look at equality of ratios and this equality of ratios. Here we have QH square is to QM square. Here also we have QM square. So we can combine these two proportionalities. So QH square is to QM square is to AN times A prime N is equal to KR square is to OR square. But here we have OD square. But OR is equal to OD. So we can say KR square is to OR square or OD square is to AC square. Which means X equally we can say QH square is to AN times A prime N is equal to KR square is to AC square. So now KR square is to AC square is equal to BC square is to AC square, which can be written as AC times A prime C because they are equal. And KR is equal to BC. So QH square is to AN times NA prime is equal to PN square is to AN times NA prime. Why? Because BC square is to AC times A prime C is equal to PN square is to AN times NA prime. So which implies that QH is equal to PN. Why? Because they both are having the same ratio with a third quantity or magnitude. So that means PQ is parallel to MN, which is in turn parallel to CO, or we can also say CK. That means if we join P and Q, PQ is a generator and the cylinder generated passes through P, a point on the ellipse. So we have shown that any point P on the ellipse appears on the surface of the cylinder generated by PQ. So let me just generate it once more so that you get an idea. That was proposition number 9 of works of Archimedes, specifically from on conoids and spheroids. Again, let me remind you, there is a link to a PDF book which describes all these propositions in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now.